Large steering gears come in rotary vane and Rapson slide types. The rotary vane type operates as follows. Hydraulic pressure from the vane pump installed on the pump unit is conveyed via a control valve to the rotor housing. The rotary housing interior is divided into the port side and starboard side hydraulic oil chambers. For example, when turning to the port side, oil is fed into the port side hydraulic oil chamber. Here is a list of parts and seals for the actuator bottom. Let's look at parts and the structure of the rotary vane type steering gear as we assemble it. First, insert the rotor. Insert vertical seals for vanes. Insert seals for segments. Insert cover sealing rubber. Insert plate springs into vertical seals for vanes. Insert horizontal seals for vanes. Insert plate springs into vertical seals for segments. Restore the cover. Insert the rod seal. Insert sealing rubber for the gland. Put the gland seal in place. Attach the defensive valve. Attach the rudder angle indicator. Connect the pump unit to the steering gear. Bleed the steering gear of air before starting operation. Give it a test run. Confirm turning of the rotor with the rudder angle indicator. The following are typical cases of trouble with rotary vane type steering gears. Hydraulic oil leakage from the gland seal, hydraulic oil leakage from the lower seal, and wear of leakage oil seals. The following precautions must be taken when operating rotary vane type steering gears. Check abnormal sounds, vibrations, overheating, oil temperatures, and leakage. Changes in the oil amount. The motor's current values and fluctuations. The hydraulic pump's discharge pressures and fluctuations. Regular inspections of system oil properties. Regular inspections of the return filter. And confirmation of grease supply conditions for the gland seal. Rapson slide type steering gear drives the cylinder ram with hydraulic pressures from pump units. It moves the ram to the right and left by synchronizing hydraulic pressures from the pair of right and left pump units. Since a tiller, which uses the steering shaft as its rotation axis, is in contact with the ram pin, the steering shaft rotates as the ram moves right and left. Here, we have reproduced the ram movement using a test machine. This is a schematic diagram of a 2-ram, 4-cylinder Rapson slide type steering gear. You can see pressure oil being sent from the hydraulic pump in the pump unit. The torque motor is controlled by steering angle deviation signals given by the steering stand. It delivers pressure oil to specified hydraulic cylinders, thereby moving the ram and rotating the steering shaft. The Rapson slide type comes in the following models. The following cases of trouble have been reported. Switching failure of solenoid valves in the hydraulic circuit, oil leakage from the ram's gland packing, and coming off of the ram pin. The following precautions must be taken when operating Rapson slide type steering gears. Check abnormal sounds, vibrations, overheating, oil temperatures, and leakage. The oil amount and changes. The motor's current values and fluctuations. The hydraulic pump's discharge pressures and fluctuations. Regular inspections of system oil properties, and regular cleaning of the suction strainer. Hydraulic pumps and motors are vital components used to drive steering gears and mooring equipment. Screen shows the model of the bent axis type variable displacement axial piston pump for steering gears and consists of the following parts: the drive shaft, cylinder, roller bearing, valve plate, oil seal, and so forth. The cylinder block rotates as the drive shaft turns. When the rotating cylinder block is inclined toward the drive shaft core, the piston makes a reciprocal motion inside the cylinder per rotation of the cylinder block, thereby drawing in and discharging oil. This pump is of a variable displacement type and is able to change the cylinder's tilt angles. When used with steering gears, it is incorporated in the oil tank. The swash plate type axial piston pump for hydraulic deck machinery consists of the following main parts: the drive shaft, cylinder block, piston, tilting box, swash plate shaft, and valve plate. Used as hydraulic pumps for deck machinery, this type of pump has a piston whose direction of motion is in parallel with the cylinder block's rotation shaft core. As the tilting box tilts, each piston makes a reciprocal motion within the cylinder each time the cylinder block makes a rotation, thereby drawing in and expelling the liquid. The following cases of trouble have been reported: wear of the pump regulator, and oil leakage due to damaged oil seal. The following precautions must be taken when operating hydraulic pumps. Check for oil leakage from parts. Look for a significant rise in oil temperatures. Inspect oil properties regularly. Listen for abnormal sounds heard during operation. And inspect the magnet strainers in pipes regularly. The hydraulic motor for deck machinery use has a part structure as follows. The casing has cylinders in the radial direction, and the flange part is provided to secure oil passages to the cylinders and to fix the motor. The valve housing is fixed with bolts across a spacer in which a valve spool rotates. The crankshaft is supported by two taper roller bearings, the other end of it being connected to the output shaft. With this hydraulic motor, A and B ports are provided to serve as the inlet for high-pressure hydraulic oil or the tank-connected outlet for the oil. The motor's rotational direction is determined by which port the hydraulic oil is sent. When hydraulic oil is sent to A port, hydraulic pressure is applied to the upper part of the piston and generates a force to push down the piston, allowing the crankshaft to rotate. The valve spool, which is connected to the cross coupling, rotates accordingly. Then, the oil feeding port positions change, allowing the hydraulic pressure to be applied to the next cylinder in the rotational direction. Port positions for discharge change likewise. Repetition of these motions keeps the crankshaft rotating. The following cases of trouble have been reported: cracking of the cylinder block, oil leakage and damage to the oil seal, and foreign matter contaminating the hydraulic oil. The following precautions must be taken when operating hydraulic motors. Conduct regular inspections of oil properties. Watch out for oil leakage. Make sure to conduct complete flushing after repairs. And operate the motor very carefully in cases where the handle must be abruptly manipulated or the operator can lose control due to stormy weather or other unexpected external factors. To properly operate and manage onboard auxiliary machinery, it is essential that you fully understand and grasp machine structures by reading maker-provided instruction manuals and referring to trouble case studies. You are also advised to prepare for maintenance plans well in advance by making inquiries with the manufacturer if specific operational conditions lead you to suspect trouble may.
I'll explain the measuring procedure of crankshaft deflection when overhauling the main bearing or when running the engine every 2,000 to 2,500 hours. If the crankshaft deflection is expanded, the crankshaft may be broken and may result in an accident. Consequently, periodically measure the crankshaft deflection. Make sure to measure it when cooling engine. Measure the deflection by the exclusive tool. Open the pressure indicator cocks of all the cylinders. Turn the flywheel to bring the crank pin to the position EB of 30 degrees after the bottom dead center. EB is the exhaust bottom and the position of measuring reference. In this condition, fit the deflection gauge to the set needle of dial gauge to point 0. Slowly turn the flywheel. Measure and record readings of the dial gauge in order of exhaust side, top, pump side, and pump side bottom. If necessary, read the needle of dial gauge by the deflection mirror. Measure in all cylinders and the work is finished. The relation between the deflection value at each measured position with reference taken at the first point and the crankshaft is as shown. Allowable value of the deflection is as shown. Deflection increases every measurement and it exceeds allowable value, you need to check the main bearing metal and correct the deflection.
The variable injection timing system comprises VIT actuators located on the fuel pumps and pneumatic components located on the control console at the side of the engine. Supply 7-bar control air pressure to the pneumatic components on the engine side console. Switch control from the engine room to the engine side console. Turn the regulating hand wheel until the tapered slots of the two levers are aligned. The throttle non-return valve must be fully open before adjusting the VIT system. Loosen the lock nut and screw the spindle counterclockwise as far as it will go. Make sure that the pressurized air reaches the VIT actuator. It may be necessary to switch the changeover valve manually. The pilot valve must be adjusted so that when the spindle is pressed 8 mm inwards, the control air pressure will be 5.5 bar. Turn the regulating handwheel so that the steel bar just touches the pilot valve. Insert a distance piece with a thickness of precisely 8 mm. If the control air pressure deviates from 5.5 bar, loosen the lock screw and turn the spring retainer cap of the pilot valve until the pressure, which can be read on the pressure gauge on the engine side control console, reads 5.5 bar. Note that it will not be possible to obtain the correct pressure if the throttle non-return valve is not fully open. Screw the spindle clockwise until a pressure drop can just be registered. Screw the spindle counterclockwise 1 revolution and lock it in this position with a lock nut. This position prevents a sudden increase in VIT index and thereby a sudden increase in the maximum combustion pressure. Make sure that the VIT index is set at 0. Measure distance R between the two pivoting points. Note down the result. Measure distance L between the pivoting point and the center line of the VIT rack. Note down the result. Measure distance X between the pivoting point and the center line of the VIT rack. Note down the result. To ensure that the movement of the link is evenly distributed around the center line of the VIT rack, R must equal L plus X. In the event that R does not equal L plus X, displace the lever until new measurements confirm that R equals L plus X. When the correct position is obtained, mark the position of the lever and stamp the cylinder number on the locking plate and lever. Turn the regulating handwheel until the pressure on the pressure gauge reads 2.75 bar. The VIT rack must be adjusted so that the middle index of the VIT rack can be read when a control air pressure of 2.75 bar is applied. If the actual VIT index does not correspond to the middle index, adjust the link until it does. Start the engine and run it up to a load corresponding to the breakpoint load. Use the indicator drive or PMI system to adjust the load until it corresponds to the breakpoint load. The mean indicated pressures of the individual cylinders must not deviate more than 0.5 bar. If the deviation is more than 0.5 bar, adjust the load distribution on the fuel index rack of the individual cylinders. The engine is now running at the brake point. At this load, the steel rod must touch both pivoting points. If the rod does not touch both pivoting points, adjust the rod in accordance with step 2.3 of this film. Measure the maximum combustion pressures of each cylinder. Adjust the links or disconnect and lock the VIT racks so that the maximum combustion pressures, corrected to ISO ambient conditions, are uniform and have the required values. Note down the fuel pump indexes and VIT indexes. Run the engine up until it corresponds to 100% MCR. Use the indicator drive or PMI system to adjust the load so that it corresponds to 100% MCR. The mean indicated pressures of the individual cylinders must not deviate more than 0.5 bar. If the deviation is more than 0.5 bar, adjust the load distribution on the fuel index rack of the individual cylinders. Again, measure the maximum combustion pressures for each cylinder. Adjust the links or displace and lock the VIT racks so that the maximum combustion pressures, corrected to ISO ambient conditions, are uniform and have the required values. Note down the fuel pump and VIT indexes. Note down the VIT indexes at brake point and 100% MCR and calculate the average index. Determine the middle value of the VIT rack and calculate the difference between the middle index and the calculated average index. The result of this calculation will determine how much the cams are to be turned. If the result exceeds 0.5 millimeters, the cams must be turned according to step 1.6 of this film, after step 1.5 has been completed. The purpose of turning the cams is to distribute the brake point and 100% MCR service points evenly around the middle value of the VIT rack. Note down the VIT indexes at brake point and at 100% MCR and calculate the difference. Add half of this difference to the middle value of the VIT rack. Subtract half of this difference from the middle value of the VIT rack. Calculate the average VIT index at brake point and at 100% MCR. Determine the control air pressures corresponding to the average VIT index at brake point and at 100% MCR. Stop the engine before making any adjustments. Make sure that control air is able to pass the changeover valve. Supply a control air pressure of 7 bar to the pilot valve. If the links were adjusted in step 1.4, then adjust again so that a control air pressure of 2.75 bar corresponds to the middle value of the VIT rack. Turn the fuel regulating handle to the brake point position. At this position, the steel rod touches both pivoting points. Displace the pilot valve bracket until the calculated control air pressure at brake point is obtained. Turn the fuel regulating handle to the 100% MCR position. Displace the lowermost pivoting point until the calculated control air pressure at 100% MCR is obtained. Start the engine and run it up to a load corresponding to the brake point. Make sure that the control air pressure is able to pass the changeover valve. Fine adjust the links so that the maximum combustion pressures, corrected to ISO ambient conditions, are uniform and have the required value. Load the engine until it corresponds to 100% MCR, and fine adjust the lowermost pivoting point so that the maximum combustion pressures, corrected to ISO ambient conditions, are uniform and have the required values. Cams must be turned if the value calculated in step 1.4 of this film is exceeded. The actual fuel pump lead must be determined before turning the cams. Make sure that the reversing links are in the ahead position. Disconnect the air pipe and remove the cover from the puncture valve. Remove the plug screws to provide access for the measuring tool. Remove the puncture valve. Mount the measuring tool, making sure that it engages correctly with the bore in the top of the fuel pump plunger. Turn the cylinder concerned to top dead center. Read the actual fuel pump lead directly on the measuring tool. Read the VIT index. If the VIT index is not at 0, the lead must be corrected before it is recorded in the engine logbook. Carry out fine adjustments through the small cover. If the camshaft has been dismantled or if new cams have been mounted, adjust the cams before mounting the lower part of the camshaft housing. Remove the plugs from the cam and insert copper gaskets. Mount, but do not tighten the snap-on couplings. Connect the snap-on couplings to the high-pressure pump and vent the system. When oil without air bubbles flows from the couplings, fully tighten the couplings. Turn the engine until the special spanner can be mounted, then raise the pressure until oil seeps out between the cam and camshaft. Read the measuring tool once again before turning the cam. Turn the cam in the required direction. See also step 1.4 of this film. Follow the turning of the cam on the measuring tool and stop turning when the required change has been obtained. Relieve the system of pressure and remove the spanner and hydraulic tools. Leave the cams to settle for a minimum of 15 minutes and then mount the plugs. Turn the cylinder concerned to top dead center and read the new fuel pump lead. Read the VIT index. If the VIT index is not at 0, the lead must be corrected before it is recorded in the engine logbook. Mount the cover of the camshaft housing. Provide the puncture valve with new sealing rings and lubricate with molybdenum disulfide. Tighten the puncture valve to the torque stated in the instruction book, Volume 2, Chapter 909, and mount the plug screws, cover and control air pipe. Finally, change over to normal engine control. Make sure that the VIT system changeover valve is properly connected. The system will have to be adjusted when certain components are replaced. Regarding the throttle non-return valve, see Part 1, Step 1.1 of this film. Regarding the pilot valve, see Part 1, Step 1.1 of this film. Regarding the VIT actuators, see Part 1, Step 1.2 of this film. Measure the maximum combustion pressures regularly, especially after bunkering new fuel oil. Adjust the individual links until the maximum combustion pressures, corrected to ISO ambient conditions, are uniform and have the required value. If all the maximum combustion pressures are either too high or too low, displace the pilot valve bracket. The purpose of this adjustment is to keep the brake point at the selected engine load and to control the pressure increase. An excessive pressure increase may lead to a poor cylinder condition. In this event, contact the engine builder before making any adjustment. Start the engine and run it up to a load corresponding to the brake point load, and hereafter to 100% MCR load. Use the indicator drive or PMI system to adjust the load so that it corresponds to the brake point load and 100% MCR load. Note down the fuel pump indexes. The mean indicated pressure of the individual cylinders must not deviate more than 0.5 bar. If the deviation is larger than 0.5 bar, adjust the load distribution on the fuel index rack of the individual cylinders. Switch from engine room control to control from the engine side console. Turn the fuel regulating hand wheel corresponding to the determined fuel pump index at brake point. If the steel rod does not touch both pivoting points, loosen it from the shaft and turn it to the correct position. Start the engine and run it up to a load corresponding to the brake point load. Make sure that the steel rod touches both pivoting points. Adjust the links until all maximum combustion pressures are uniform, and then displace the pilot valve bracket until the average combustion pressure, corrected to ISO ambient conditions, is at the required value. Load the engine so that it corresponds to 100% MCR load and displace the lowermost pivoting point until the average combustion pressure, corrected to ISO ambient conditions, is at the required value. Decrease the load until it corresponds to 40 to 50% MCR load and displace the uppermost pivoting point until the VIT racks just start to move inwards. This occurs at a control air pressure of about 0.5 bar. Lock the pivoting point in this position and change over to normal engine control. All spindle guides are function tested before they are delivered. All fuel valves are assembled and function tested before leaving the workshop. Overhauled fuel valves or fuel valves taken from stock must be function tested before they are mounted in the cylinder cover. The pressure testing pump is equipped with pressure gauges for displaying opening pressure, working pressure, venting function and air inlet pressure. Position the fuel valve in the test rig. For guidance on how to operate the pressure testing pump, refer to the supplier's special instructions. To ensure that over-tightening has not taken place, check that the locking and indicating pins have not been bent or broken off. In the event of over-tightening, mount a new spring housing. A very important element in the correct functioning of the fuel valve, both during testing and in service, is ensuring that the spring housings apply the predetermined tightening force. To ensure that this force is present, a special tool has been designed to check the calibration of the spring housings. We recommend that the calibration of new and especially old spring housings be checked before they are mounted on the engine or on the fuel valve test rig. Tighten the nuts until the top face of the pressure disc is flush with the top face of the spring housing. Fuel valves are available in 3 different designs depending on engine size. Refer to your instruction book to see which valve is to be used on your engine. The pressure testing procedure is the same for all types of valve. Slowly fill the valve by pumping at low pressure until fuel oil, without air bubbles, flows from the fuel oil return pipe. Raise the pressure until it is above the opening pressure. Flush the valve for about 5 seconds. There will always be a certain amount of fuel oil flowing from the fuel oil return pipe when the fuel valve is full of fuel oil and pressurized. Fuel oil must not seep from the fuel valve nozzle holes until reaching a pressure of 50 bar below the specified opening pressure. If the fuel oil does seep from the fuel valve nozzles, see Instruction Book Volume 2, Chapter 909. Pump 5 to 10 strokes to fully open the valve and to blow out any dirt. Then relieve the pressure. Slowly increase the pressure until fuel oil is emitted from all the atomizer holes. Read the actual opening pressure on the pressure gauge marked opening pressure. Compare the actual opening pressure with the pressure specified in the instruction book, Volume 2, Chapter 909, and, if necessary, adjust the pressure by inserting or removing discs. Set up the thrust spindle in a bench vise with soft jaws. Compress the spring for the thrust spindle to remove the tension on the circlips, and then remove the circlips. Do not insert more than 5 extra discs when adjusting the pressure. The sum of the pressure markings on the extra discs must not exceed 150 bar. The fuel valve must be retested after any adjustment. If the quick pressure drop cannot be registered, the slide is sticking, or the hole is blocked. Disassemble and examine the parts, replace if necessary. Slowly fill the valve by pumping at low pressure until fuel oil, without air bubbles, flows from the fuel oil return pipe. Remove the fuel oil return pipe and block the outlet hole with a gasket and a plug screw. Increase the pressure to about 100 bar and move the control handle to the closed position. The pressure should now remain at 100 bar. If oil leaks at the union nut, replace the O-ring seal of the valve head. If oil leaks at the lower end of the valve, replace the O-ring seal on the spindle guide. After the fuel valve has passed all the tests, it can be mounted in the cylinder cover. The main objective of the normal tests shown in part 3 of this film is to ensure that the valves function at the correct opening pressures and that they seal tightly. As the injection capacity of the engine fuel pump is much greater than that of the pressure testing pump, atomization will be ensured during service, provided that the fuel valve passes the normal tests. The computer-controlled injection system, which is able to simulate the injection into a diesel engine, comprises a high-pressure booster pump, a servo fuel pump unit, and a computer control and monitoring system. Quality controlled spare parts from MAN B&W Copenhagen will ensure continuous and reliable operation.
Control and adjusting of the valve clearance. Safety precautions and preparations. Shut off the starting air. Shut off the fuel oil. Stop the lubrication oil circulation. Remove the top cover to give access to the valves. Remove the cover for valve camshaft. Turn the crankshaft until the cylinder is in ignition top dead center. That means both valves are closed and the cams are on the circular part. Check that the surfaces are clean. Loosen the counter nut and the adjusting screw on the rocker arm and insert the feeler gauge between the valve bridge and the rocker arm. Adjust the screw on the rocker arm until the feeler gauge gives only slight resistance. Tighten the counter nut on the valve bridge with torque. See the value on page 500.40. Recheck that the feeler gauge clearance hasn't changed. Adjust the screw on the valve bridge until the feeler gauge gives slightly more resistance. But it must still be possible to move the feeler gauge. Loosen the counter nut and the adjusting screw on the rocker arm and insert the feeler gauge between the valve bridge and the rocker arm. Adjust the screw on the rocker arm until the feeler gauge gives only slight resistance. Tighten the counter nut on the valve bridge with torque. See the value on page 500.40. Adjust the screw on the valve bridge until the feeler gauge gives slightly more resistance. But it must still be possible to move the feeler gauge. Mount the top cover on the cylinder cover. Mount the camshaft cover.
The engine has two cooling water systems. One high temperature jacket water system and one low temperature system. Only the high temperature system will be described here. The high temperature system is a fresh water cooling system. During operation or just after the engine has been stopped, most of the engine will be hot. Touching the engine parts may cause burns. In this system, be especially aware of the following parts. Cooling water pipes may get up to 90 degrees Celsius. The operator should always be aware of the high water temperature when working with parts of the cooling water system. Pay attention to how the additives are stored. The additives to the cooling water may involve a health risk, especially when highly concentrated. The operators are responsible for keeping updated with the producer's warnings on the containers or data sheets. Parts of the engine to be cooled by the jacket water system is the cylinder block, the cylinder liners, the cylinder heads and the turbocharger. Control of cooling water quality is very important to prevent corrosion, sediments and surface growth in the jacket water cooling system. It is important to use inhibitors in the jacket water, both for fresh water and for distilled water. When using inhibitors, the service instructions have to be followed very carefully with respect to the water quality, supplement volume treatment and storage. Changing high temperature cooling water. Empty and flush the cooling system thoroughly before commencing treatment to remove as much sludge and rust as possible. If the system is exceptionally rusty, it is advisable to repeat this procedure after the first week or two of treatment. Click the components for further information. The jacket water pump is an engine-driven centrifugal pump type. It delivers water for cooling the turbocharger and the high-temperature section of charge air cooler for engines equipped with two-stage charge air cooler. The roller bearings are lubricated by the main lube oil system. Do not operate without proper water supply. This will destroy the pump. If observing lubricating oil or water coming through the telltale hole, replace both sealing rings to ensure satisfactory sealing. The heater module consists of an electric pump with an electric element. The purpose of the heater module is to keep the engine temperature at approximately 50 degrees Celsius while the engine is in standby mode. Never operate without proper water supply, because that will destroy the ceramic seals in the pump immediately. The purpose of the regulating valve is to adjust the jacket water flow rate. The jacket water cooler removes heat from the jacket water and transfers it to the raw seawater system. The plate heat exchanger consists of edge-clamped frames within which a number of plates and gaskets are compressed. It is of great importance to inspect the high-temperature water cooler during the running-in period, in order to gain experience to determine the correct intervals for cleaning. When the cooler is out of operation for a longer period, empty it, open it and clean it. Cleaning of the plates is important to restrict corrosion and to keep the heat transfer rate at a maximum level. Plate exchangers should be inspected and cleaned at regular intervals. fire. There will always be a certain danger of fire when running a diesel engine. A combination of leaking fuel oil and hot engine parts may start a fire that can be very damaging to the engine and in some cases dangerous to the engine crew. Leakages in the high-pressure part of the fuel system may create situations where the probability of a fire increases. It is of utmost importance to undertake inspections of these parts and carry out preventative measures against this on a regular basis. Thermal hazards. Fuel oil pipes may be very hot and should not be touched, even though they are insulated. Be aware that fuel oil pipes leading from the heavy fuel oil feeder booster module to the engine may be steam traced. When performing maintenance on the fuel oil system, remember that heavy fuel oil is very hot. Fuel oils are flammable and should be treated with care. They may also irritate skin, so rinse off fuel oil as soon as possible. Take note not to wear clothing that is soaked with oil. All Ulstein Bergen main and auxiliary engines can be operated on heavy fuel oil under certain conditions, which include heavy fuel oil and lubricating oil quality, and the equipment which is needed. A safety and indicator valve is fitted outside the cylinder head. By means of this valve, the maximum pressure in each cylinder should be measured once a month. The measuring must be carried out with 100% load on the engine. Log the maximum combustion pressures and exhaust temperatures. Find causes and rectify if combustion pressure in one cylinder differs more than 3 bar from the average maximum at full load. Abnormal change in the exhaust temperature of one cylinder is indicated. Click the components for further information. The feeder booster module feeds heavy fuel oil to the engines. The module consists of equipment ensuring that the fuel oil is correctly filtered and that it will have the correct temperature and viscosity when entering the engine. The feeder booster module consists of the following main components: 2 suction strainers, 2 feeder pumps of which one is a standby pump, mixing pipe, de-aeration vessel, 2 booster pumps, of which one is a standby pump, 2 fuel heaters, automatic filter with separate manual bypass filter, viscosity control system, duplex fine filter, the oil temperature and oil pressure on the fuel oil outlet should be recorded every day. changeover valve is equipped with a switch for heavy fuel or diesel oil operation. A light indicates that the engine is running on marine diesel oil or heavy fuel oil. Oil in the disconnected fuel oil system can circulate through the valve and is thereby kept heated to correct temperature. The cock enables switching between the filter elements, enabling replacement while the engine is in operation. In addition to logging the fuel oil pressure after the filter elements have to be checked at least once a month. How often they have to be replaced depends on the fuel oil quality. Make sure that the filter that is going to be dismantled is not in operation by checking the cock position. Open the vent plug. Empty the filter housing of diesel oil by unscrewing the plug. This is not necessary for checking the element. Unscrew the nuts and remove the cover. Remove the filter element from the housing and check the element. Wash out all oil sediments in the filter housing. Blow the housing clean with compressed air. Place the text in the correct sequence. Wrong. You have no more tries. We will show you the answer. Put the new filter element into the filter housing. Fit the cover with the nuts. Vent the filter by turning the vent plug 1 revolution until pure oil flows out of the drain pipe connected to the nipple. Further venting is done by loosening the plug until the oil is free of air bubbles. Assure that pipe couplings and plugs are tightened and that there are no leakages from the filter housing. The fuel oil injection pumps inject the correct amount of fuel into the combustion chamber via short high-pressure pipes and the injection valves. The pumps are driven by the camshaft via the push rods and regulated by the regulator via the link arms. All engines running on heavy fuel oil are equipped with a cleaning system for the fuel injection pumps. It is of great importance to check the control levers and fuel pump racks weekly for sticking. Tightening torques for nuts on high-pressure fuel pipes must be inside the tolerance given. Too high tightening may lead reduced flow of fuel to the cylinders due to narrowing of the pipes. All engines running on heavy fuel oil are equipped with a cleaning system for the fuel injection pumps in order to prevent the control rod and sleeve from getting dirty and sticky. The fuel injection pump cleaning system should always be operating when running on heavy fuel oil. After cleaning or overhaul of the fuel injection pumps, start the cleaning system before the pumps. Check the level in the diesel oil tank. The fuel oil injection valves should provide the injection of fuel oil to the combustion chambers. When operating on heavy fuel oil, the nozzles have to be cooled. This is done by the nozzle temperature control system. A nozzle should not be disassembled for inspection or changed unless the single cylinder exhaust's temperature deviates considerably from the average. Please click the graphic showing the correct behaviour of the fuel injection nozzle during injection. High exhaust temperature in one cylinder may be caused by leaking valves, incorrect injection timing, or a leaking nozzle. The problem is easily identified by switching two valves and observing if the problem follows the nozzle. The cooling medium in the nozzle temperature control system is oil. A nozzle should not be circulated also when the engine is running on diesel oil. The coolant temperature must be kept within the prescribed limits. Too low temperature may cause corrosion on the nozzles. Clean the filter once a week by turning the handle on the filter housing. The heat exchanger uses high temperature jacket water for cooling. It is fitted with corrosion plugs which must be checked and be replaced in case of leakage. The nozzle coolant has to be circulated also when the engine is running on diesel oil. The coolant temperature must be kept within the prescribed limits. Too low temperature may cause corrosion on the nozzles. Click the components for further information.
Pump leakage, a natural occurrence found in all types of industry today. If not controlled, it creates costly problems that affect you directly. Problems of pollution, a potentially destructive force affecting the environment inside and outside your plant. Corrosion and bearing fatigue, devastating factors destroying equipment and reducing efficiency. Product loss, increasing costs and decreasing profits. Maintenance requirements, resulting in wasted inventory and the inefficient use of labor. Leakage, slowly eating away at your business productivity. Many industries today attempt to control leakage by using braided packing. Where packing may be ideal in some situations, it is not in others. Since packing must leak in order to work effectively, it is not recommended for use in industries that follow strict environmental regulations, such as chemical, food processing, pharmaceutical, petrochemical. Here, leakage-related results such as pollution, corrosion, and loss of product cannot be tolerated. But Garlock, the industry leader in sealing products, realizes this and responds with mechanical seals, the solution to these problems and more. Mechanical seals uniquely designed to eliminate leakage, offering convenience and cost-saving benefits in many areas. Mechanical seals cut down on pollution, ensure worker safety, reduce maintenance and house cleaning costs, and stop valuable product from going down the drain. But the benefits don't stop there. Mechanical seals dramatically improve the life of bearings. Mechanical seals create less friction, increasing shaft and sleeve life by eliminating wear associated with braided packing. And mechanical seals reduce product dilution, saving you money. To realize all of their benefits, let's take a closer look at how a mechanical seal operates. Contrary to popular belief, mechanical seal design and operation is relatively simple. Basically, it consists of two flat faces, one stationary, mounted in the gland, and one rotating with the shaft in a circular motion. Next, spring pressure is incorporated to help hold the faces together. This spring pressure also serves to compensate for end play and some shaft runout. Finally, secondary sealing elements are added to prevent leakage along the shaft and around the stationary face. These secondary sealing elements meet a wide variety of applications and are available in several styles and materials. Now, the seal design is complete, an assembly that stops leakage in the three critical areas. At seal faces, at the face of the stuffing box, and under the seal along the shaft. During mechanical seal operation, fluid pressure inside the stuffing box forces the two sealing faces closer together, while providing the faces with a lubricating film, reducing frictional wear across the faces. This minute amount of fluid would be considered leakage. However, the frictional heat generated by the faces causes the fluid to evaporate. Now that you have a basic understanding of seal operation, let's talk about the seal types. Mechanical seals fall into three distinct categories: inside or outside single-mounted seals, double seals, and cartridge seals. Inside or outside single-mounted is determined by the position of the rotary portion of the seal assembly. With inside seals, the rotating assembly is mounted in the stuffing box of the pump and is completely surrounded by the fluid it seals. This fluid helps to cool the mating faces. The fluid's hydraulic force keeps the faces in contact. And solids in the fluid are thrown away from the faces by the centrifugal force. Outside seals are normally used when the material being pumped is corrosive or detrimental to the entire seal assembly. By locating the seal outside of the stuffing box, all corrosion-prone elements of the assembly are exposed only to the atmosphere. And because the entire rotary assembly is readily accessible, it's easy to install, inspect, and maintain. Outside-mounted seals are also ideal for non-metallic pumps because together they offer superior corrosion resistance. The second category, double seals, are recommended when the fluid being pumped is a poor lubricant, abrasive, or a combination of both. A double seal, consisting of an inboard and outboard assembly, allows the introduction of a pressurized, clean lubricating fluid, thereby isolating the product in the stuffing box and the injected fluid in the stuffing box from the atmosphere. Because of this ability to isolate, double seals are also recommended for services that are toxic, flammable, or detrimental to the environment. The third category, cartridge seals, combines all components into a preset assembly that is easy to install. This eliminates the need for time-consuming complicated measurements and handling. All cartridge seals come in either single or double versions and are often the most economical choice when converting from packing to a mechanical seal. In order to meet a wide variety of applications, each of these three distinct seal categories are available in unbalanced or balanced designs. An unbalanced seal allows all of the fluid pressure in the stuffing box to act as a closing force on the faces. This particular design is most effective in low-pressure applications. For high-pressure applications, however, a balanced seal is required. Here, a change in the face configuration allows some of the fluid pressure to be redirected, offsetting the total closing force on the faces. This reduction generates less heat and normally extends the seal life. Garlock, the leader in providing quality sealing products for the past 100 years, offers an in-depth line of cost-effective mechanical seals. Mechanical seals that are specifically designed to meet the critical service requirements demanded by today's industries. But a seal is just a seal if it isn't supported by innovative people. And the Garlock people, with their commitment to service and to quality, deliver the outstanding performance you expect and deserve. Mechanical seals. Eliminating pump leakage, controlling costly maintenance problems, saving you time, money, and energy. And Garlock, the sealing experts, providing the right product for your application.